Alright, we've looked at vector equation of line. Now we're going to have a look at how we represent a line segment with endpoints A and B. A and C. So a line segment doesn't extend forever. So imagine we've got origin here. Here's vector A. Here is vector C, position vector C. And we want to work out an equation for that line segment. Okay. So the way we work out line segments is that we restrict the parameter, and the parameter is lambda. We restrict lambda in the vector equation. So notice that if you set lambda equal to 0 here, you would get r is equal to a. So you would be at the beginning point. And also if you let lambda equal to 1, you would have c minus a there, and that minus a will cancel with the plus a at the front. So if lambda equals to 1, you'll get r is equal to c. Okay, and if lambda equals to anything between 0 and 1, for example, lambda equal to a half, you would be halfway between the two. That would be your r vector there. Okay, so the key thing is you restrict lambda between 0 and 1. It moves from A to C there. For all other values of lambda, you'd be outside the line segment. So find the vector equation of line segment AB where A is equal to 1, 4 and B is equal to 3, 9. So this is a 2D question, but you can still apply this to 3D. Just be careful, the direction vector is not the position vector of B. Remember, you got to do a vector subtraction of the 2 points to work out the direction vector. So here I might call the direction vector D or something to avoid confusion. Okay, so we need a point that gets me to the line, 1, 4, and we need a direction vector, which will be the other vector, minus 1, 4. Okay, so 2, 5. So therefore, my line segment is going to be A plus lambda B, or well, here it's lambda D, where lambda goes between 0 and 1. That'll give me the segment. So it's going to be 1, 4 plus lambda times 2, 5. Okay, so you can quickly check if lambda is 0, you get 1, 4, which is A. If lambda is 1, you would get 3 and 4 plus 5, 9, which is B. Okay. On the final line, I'd still write down the restriction on lambda. So that restriction there makes it a line segment. Okay, so that's line segments. Next, let's look at parametric equations. Okay, if you write r as x, y, z, you can get 3 separate equations for each of the components. Okay, so x is going to be a1 plus lambda b1. Okay, you can get similar equations for y and z. They're parametric equations, and the parameter is lambda. Okay, determining if a point lies on a line in 3D, use the vector equation to compare components on both sides. If you get the value of lambda the same in all cases, the point must lie on the line, otherwise it does not. Okay, so you sub in the point and you should get the same lambda value. Let's do a question, it'll make a bit more sense. The line passes through those 2 points. Write a vector equation for the line. So we've got an A value here, negative 2, 1, 5. Now remember, B here is not the direction vector. I'll use the letter D just to have a different letter here to be the direction vector. So 6, 3, negative 4, and then we're going to minus the A, so negative 2, 1, 5. By the way, this D is not conventional. The syllabus actually just redefines B. The syllabus redefines B to be AB, which is a bit, that's in the syllabus, so that's a bit interesting. Okay. So if you're using D here, I would call it direction. Let direction vector be be D, just to let the examiner know what D is. Okay, so 8 to negative 9. I don't like this that they do in the syllabus, by the way. Yeah, it's not... There's nothing wrong with it, but I prefer, using a different letter. Alright. So write the vector equation. So we've got R is equal to A plus lambda D in this case. So negative 2, 1, 5 plus lambda 8 to negative 9. Okay. So that's A done. B. Write the parametric equations for any point on the line. So parametric equations are splitting it. So X you just read off the top basically. So it's going to be negative 2 plus 8 lambda. The Y you read the middle. It's going to be 1 plus 2 lambda. And the Z you read the bottom. So that's 5 minus 9 lambda. So they're the three parametric equations. So that's the vector equations, that's the parametric equations. The other type is Cartesian, we'll look at that later. Determine if the point C lies on the line. Okay, so we want to sub in the point and hopefully we get the same lambda. So so basically we're checking does, and I'll sub in the point for R, negative 10, negative 1, 14. Equal to negative 2, 1, 5 plus lambda 8 to negative 9. We're checking does that. Alright, so you can just, so for one particular lambda, that's important. Okay, has to be one fixed lambda. Right, so let's have a look at the right hand side. Actually, sorry. Let's say what value of lambda would work for X. We can quickly see that if lambda is negative 1, it will work. Yeah, you can either sub in the negative 10 up in this equation. So if lambda equals negative 1, let's go X is equal to minus 2 minus 8, which is negative 10, tick. Let's have a look at Y. Y equals 1 minus 2, which is negative 1, tick, that's what we wanted. And Z is equal to 5 minus 9 times negative 1, which is 5 plus 9, which is 14, tick. Therefore, since they all worked for the same lambda value, the point negative 10, negative 1, 14 does lie on the line. Okay, now if I would have subbed in that lambda is negative 1 and it worked for 2 out of the 3, that point wouldn't lie on the line. Okay, so it's got to work for all 3, X, Y, and Z. Alright. Next question. Find a vector joining the points negative 1, 1 and 4, 11. So my A will be negative 1, 1. My B direction vector minus, so 4, 11 and minus negative 1 and minus 1. So that's going to be 5, 10. Okay, so therefore R is equal to A plus lambda B. R is equal to negative 1, 1 plus lambda, and B is 5, 10. Now, let me just make a comment. This B is 5, 10. Remember that a direction vector is anything that's parallel to the line. So here, this 510, you can actually simplify it if you like and make the numbers smaller. So if you go 5 in the horizontal component and 10 here, that's just a gradient of 2, right? That's the same as if, 2 and 1. So you could have used a b value of 1 and 2, 1 across, 2 up there. And that would simplify things a little bit. And I'd encourage you, if there's a common factor, for b, you can just pull it out, essentially absorb it into the lambda. So you could have used the direction vector of 1, 2 to simplify things a bit. I've already written 510, so I'm going to just keep going with 510, but just something to be aware of. You can do a scalar multiple of the direction vector and get another direction vector. Okay, use this to write parametric equations for any point on the line. So parametric equation, x in terms of lambda, so looking at the top, -1 plus 5 lambda, y in terms of lambda, so 1 plus 10 lambda. That's B done. C, hence. So hence suggests to use that. Find the coordinates of all points where the line cuts the parabola y is equal to x squared. Alright, so there's a couple of ways to do this, but I'm gonna eliminate the parameter, so I'm gonna solve these simultaneously. So for equation 1, I'll make 5 lambda the subject, and that's x plus 1, and then I'm gonna sub that into equation 2, and equation 2 is, to get a 5 lambda there, it's 2 times 5 lambda, so it's 1 plus 2 bracket x plus 1. So y is equal to 2x plus 2 plus 1. So y is equal to 2x plus 3. And I'm basically solving y equals 2x plus 3 with the parabola y equal x squared to work out any points of intersection. So let's sub. I'll use different numbers because I've already used 1 and 2 equations. So sub equation 4 into 3. So x squared equals to 2x plus 3. Bring over one side. Now let's factorize. -3 plus 1. So x equals to 3 and x equals to -1. And they intersect on y equal x squared, so therefore if you square that, that'll be 9. If you square that, y will equal to squaring -1, you'll get 1. So therefore intersect at the points 3, 9 and -1, 1. Alright, I'll see you in the next video.